Hi folks! Today we're going to take a look at the first of several activities that my students completed on Newton's laws of motion. These activities use a 3D printed cart that I designed that has modular components that can be swapped out for different experiments. We can mount bumpers, weight sleds, seat belts, mouse traps, and other attachments for a wide range of experiments. In this video, we're going to explore how students use common materials to construct bumpers that are designed to deform upon impact. Students will try to optimize their bumper design to limit the peak force during a collision as they investigate how increasing the duration that an impact plays out over will reduce the acceleration that a passenger would experience. We'll also connect this concept to real-world applications like helmets and protective padding. And finally, I'll share my own personal experience with how impacts play out on a racetrack to reinforce the idea that the longer it takes for a person to come to a stop, the lower the force they will experience. Let's get started. We began this activity with a discussion on Newton's second law, which states that the acceleration an object experiences is directly proportional to the force acting on it and inversely proportional to its mass. In the context of collisions, the longer it takes for something to come to a stop, the lower the peak force it will experience. Students would be designing bumpers to increase the amount of time it takes for their cars to come to a stop, thereby reducing the peak impact force. It's all about buying time. This principle is everywhere, from the padding in football helmets and walls in gymnasiums to foam pits and attenuated barriers. All of these are designed to reduce the force you experience by increasing the time it takes to come to a stop. I use some of my racing experiences as examples. In one crash, I hit a wall head-on and came to a stop almost instantly, which resulted in a huge peak force that I felt for days. Then I show them an accident in which I flipped after hitting another car. The crash played out over a longer time period, and so I didn't feel a large peak force. Students begin to realize that it's not just about how fast you're going, but how quickly you become stationary. And the longer it takes for that to happen, the smaller the force you experience. Finally, I discuss my skydiving experiences and how when a parachute blossoms, you slow down very quickly, experiencing around 4 Gs of deceleration. But that's a lot nicer than the hundreds of Gs you'd experience if the parachute didn't blossom. With all that in mind, I introduce my students to the challenge. Their goal is to design a bumper that will result in the lowest peak force possible. Students are given a modular chassis with a 3D printed bumper attachment bolted on. Using a combination of hot glue, paper, cardboard, and other classroom materials, they design a bumper that they believe will limit the peak force their car experiences. The setup for this activity was pretty simple. Students would roll their cars down a ramp into a force sensor that was fixed to the bottom. We placed a mass in a weight sled that I designed to give the cars a little bit more momentum. We captured the collisions using a slow-motion camera setting on my phone so students could analyze what was happening to their bumpers and make necessary changes. To make things interesting, I decided that each of my class sections would have a different material that they'd have to incorporate into their bumper, an idea I got from my favorite 90s Japanese cooking show. We established a control using a car with a blank bumper. The peak force of the control car maxed out at around 20 newtons, so as a class, we aimed to cut this number in half and limit impacts to under 10 newtons. The best bumpers were the ones that absorbed much of the impact by deforming gradually, increasing the time it took for the cars to come to a stop. Materials like crumbled paper, layered cardboard, and foam helped spread out the force. Tissues were also very effective. If cars did not meet the 10 Newton target, students would have to redesign their bumpers. The challenge became increasingly difficult as we then aimed to keep the impacts under 8 newtons and finally 6 newtons. Several of the groups successfully met this 6 Newton target. Other groups tried some radical designs. One very curious example was this car, which used a bouncy bumper and experienced a peak force almost identical to the control car. I used this as a teachable moment on impulse and explained how a sudden change in momentum results in a much higher force. I was very impressed to see so many different designs that worked, and to watch the engineering design process play out as students tweaked and refined their bumpers to meet the target force requirements. At first, I was a little nervous that the impacts would crack the bumpers or even the chassis, but despite hundreds of tests, none of them had any noticeable damage. This has quickly become one of my favorite activities, and there is still a lot that we can do with these modular chassis. In the next video, we'll use the same carts and add a passenger compartment with a seat belt to demonstrate Newton's first law of motion the law of inertia. Hope you enjoyed the ride. Don't forget to like and subscribe.